thanks a lot for inviting me. I'm going to talk about Ray, which is a system that we've been developing at UC Berkeley with the people listed here and many others across the world. So for the motivation, let's look at the machine learning or AI ecosystem today. So there's many different tasks and many computational patterns that arise. And maybe you first think of distributed machine learning training, but there's also things like model serving or data processing, which are very important. And today, people typically build separate distributed systems for each of these. And examples for these are Horovod, for example, for distributed training, or Spark for data processing, Clipper for model serving. And these systems are extremely good at what they do, but there's a challenge for cross-cutting applications here. Often, AI applications need a lot of these capabilities at the same time. And if you have separate systems, then there's lots of difficulties that come with it. So one example for this is reinforcement learning, where you have distributed training, model serving, simulation, and also data processing. And these all are coupled with each other in a tight loop. And so using separate distributed systems is not enough. So emerging AI applications require stitching together multiple such systems. And this provides many challenges, amongst others in sharing the resources, cluster resources between systems, interoperating between these systems, transferring data across these systems, and also bringing together the various different fault tolerance models. So this often means that practitioners are building custom systems. So examples are Gorilla from DeepMind, AlphaGo, another system called Evolution Strategies from OpenAI, and other systems like this. So one motivating example for this is reinforcement learning. So there you have an environment which basically sets up the problem. So this could be something like a game simulator. Maybe you have heard of AlphaGo, which can use such a simulator to train a reinforcement learning agent. Or it could be a robot where typically there's some state. So in the case of AlphaGo, it would be the board state. In the case of a robot, it would be the joins of various effectors. And then there's an agent which acts in this environment. So the agent has a policy which maps states to actions. In the example of the AlphaGo, the state would be a board state, and then the action would be where we set the stone. Or in the case of a robot, the state would be the various joints positions, and the action would be the torques on these joints. So let's zoom a little bit more into the agent. What does the agent actually do? There's one part which is policy evaluation, which takes the state and then outputs an action. That's the part that interfaces with the external world. This part is used to collect samples, which are then fed into a policy improvement system, which is going to compute a new policy. And then the policy is again evaluated, and this is run in a loop. So we have several parts of the ML ecosystem here. The policy evaluation is really a serving system, which, given some state, computes some action. The policy improvement phase is really a training system. So here you're going to use all your data and also the reinforcements you get from the system. So how did you do, for example, in the AlphaGo game? Or did the robot do its job correctly? And then given these rewards and the states and actions, we can compute a new policy which is going to do better in the future. And then on the environment side, we do typically some data processing, and also, very importantly, we interface with lots of different simulators. So here you already have 4 of these paradigms in one application. And this all runs in a tightly integrated loop. So within seconds, you have to iterate on these things. So therefore, we need a distributed system which is very general to support all these workloads. So for example, there's different computational models. So training is compute parallel, serving is a client-server architecture, simulation again is compute parallel, and data processing often use some kind of BSP model. Then they also there's different requirements on the state. Some of these are stateful, some of them are stateless. There's very heterogeneous task durations. So for example, computing a single action could take sub-milliseconds, whereas doing a long-running training job for a neural network could take hours or even days. And so, therefore, our system needs to be very general. Here are some examples for our systems that support this. And we are really, so this is the problem, and we are providing a unified system that can support all these workloads. So instead of having separate distributed system for each of them, we use one distributed system called Ray, and then we can build all of these workloads as libraries on top of that system. Okay. So there are three things that we need to do to design such a system. So one is to unify stateless and stateful computation. Many things like data processing, for example, are more stateless. Other things like doing simulations are very stateful. So the system needs to cope with both of them very well. Then we need a unified fault tolerance mechanism for both stateless and stateful computation. And then we also need to make this very scalable. Because for AI applications, they're typically compute bound. So we need to support very high throughput in terms of, both high throughput in terms of tasks and also very low latency. Okay, so let me first talk about how we can unify stateless and stateful computation. So this is the API of the system. So if you would use it, this is how you do it. So typically people use it through Python. So in this case, we have two Python functions defined. One of them just returns 1. The other one adds 2 numbers. And this is the stateless part of the API. So what do you do now to distribute these functions? You put on this decorator called ray.remote, which makes a function into a remote function. And these functions can then be executed anywhere in the cluster. So in order to execute the function, you call function name.remote, which will immediately return with a so-called object ID of the result. And then in the background, the compute system Ray will execute it somewhere in the cluster. So we do this for 2 functions, and they produce 2 outputs, x and y. And these functions can actually now run in parallel in the background. And then we can put the results into the add function, which is just going to add them up and going to return a new output. And this, again, is an object ID. And then we can call ray.get on it, which will materialize it on the current Python process. So that might involve shipping it from a different machine, and then it will return the result. And of course, here I wrote down some very simple functions, which probably you wouldn't parallelize. But this can be used very easily to parallelize complex functions that take a long time to run. So that's the stateless part of the API. But this turns out is not enough. So while it's very simple, we often need some sort of state. So this could be because we have some third-party simulator, like a game, where we can't easily read out the state, but we need to keep it around. This could be something like a neural network, which we need to update. Or it could be something like a parameter server, which accumulates updates from the reinforcement learning or supervised learning workload. And also, we can use the state to encapsulate interactions with the real world. The real world is sort of like state that moves along. So how do we support state? We do it via a concept called actors. So this is the birthplace of Erlang, so you probably know about that. So how we express this is we use Python classes for that. So you can take some class that you've already defined, and then you put this add ray.remote decorator around it, which makes the class into a remote class. And then you can instantiate the class via class name.remote. So this will create an object of the class which will live somewhere in the cluster. And the system on the background will construct this computation graph, which first runs the constructor. And it starts off with the value of the class is 0 at the beginning, as is initialized in the cluster, in the constructor. And then, for example, we call increment on it, which will call the increment method on that actor, and then advance the state to value equal to 1. And it will also produce an output. In this case, it just returns the value. And this will again be an object ID. And then you can call increment again, which will again advance the state and return a new object. So this introduction of these stateful edges, which pass along the state in the computation, allows us to unify stateful and stateless computation. State is sort of like an extra input to the function, and it's just carry around. But this is handled very efficiently by the system. We don't need to serialize the state. It can just be kept around. And the state could, in fact, be, for example, some real-world state. So you have now seen basically the full API of the system. It's very simple. It just mirrors the way that serial applications are being built with functions and classes. And these can interoperate very nicely. So you can call functions from within functions. You can pass actors to functions, call them. You can also call remote functions in actors and so on. So the system is very general. OK, and then at the end, we can also get the result, and that will again materialize the computation. So now, of course, when you go to large scale, faults really become unavoidable. So how do we handle fault tolerance in this model? So we use, again, a unified fault tolerance model for both stateful and stateless computations. And we also recover from faults transparently. So the user in their code doesn't need to be concerned about faults, and the system will do it automatically. So how does it do that? It builds a computation graph. So it keeps track of what the computations are that have been run. For example, in this case, we have run 2 remote functions, and then we've combined the result with the add function. And when this function is submitted, the system will store the computation graph in a database called the lineage store, and it will be persisted there. And then say that a node goes down, and we lose the results x and z. Then what the system does, it goes through the computation graph. It figures out that it needs to rerun add in order to get back z, and it needs to rerun f in order to get back x. F has no dependencies, so therefore we can immediately execute it. And then after x becomes available, we can rerun add, and then we can return z to the user. Similar in the stateful case. So say we have created the actor, we have run the increment method, and now the node that stored the actor dies. So therefore, we lost the complete state associated to the actor. So then the system can again go through the computation graph. It can determine that in order to get back y, it needs to rerun the increment method. And in order to run the increment method, it needs to call the constructor again. And then, because the constructor has no dependencies, it will rerun that. That will recreate the actor, and then the system will just rerun the increment method. OK, so now this is a very nice way to provide fault tolerance for the system. But how do we scale this up? Because traditionally, these sort of lineage-based, so the lineage-based fault tolerance per se is not new. It's also used in systems like Spark or Seal. But this is typically being used on coarse-grained tasks on the order of minutes or seconds, whereas machine learning applications really need very fine-grained tasks on the order of milliseconds, and also at very high throughput. So traditionally, the scheduler and the lineage store are very tightly coupled. They're typically part of the same process. And to get the performance requirements, we just decouple them and put them into separate components. And that means we can replicate them individually. So we can have multiple schedulers. In fact, we have 1 per node in the cluster. And we can also replicate the lineage store and shard it to get very high throughput. So let me put this into the broader design of the system. So typically, we have multiple nodes. Each of them has a scheduler. And there's a number of processes. So these are typically Python interpreters, which are going to execute the code. There's one driver, which drives the whole computation and submits tasks. And then there's workers that execute tasks and can also submit tasks themselves. So we support nested parallelism. The tasks are submitted to the schedulers, which then can redistribute them. So either it can be executed on the same node, or it can be executed on a different node, depending on where the objects are and what are the compute availabilities on the nodes. We have an object store, which can be used to share memory between the workers. So this is especially important in the regime where you have many cores on each node, and there's a lot of data. So we use shared memory to efficiently share the data without serialization overhead. And then we use this global control store, which is a sharded database. So this makes it possible to make the rest of the system basically stateless. So this makes it very easy to do fault tolerance, because when a node goes down, we just need to restart it, and it can reread the information from the global control store and then just re-execute the computation. It also makes it very easy to build tools for the system. So in distributed systems, it's typically very hard to do things like debugging or profiling and things like that. And the control store has all information about what is being executed in the cluster. And so we have a web UI that can inspect these things, and you can easily log what is going on, which kind of computations are being done. So now this architecture allows us to operate at a very high scale. So we can process over 1 million tasks per second. So this here has some performance measurements on 50 to 100 node cluster. So on 100 nodes, we easily get 2 million tasks per second, for example. We can also support very low latency tasks, which is very important for both more traditional supervised learning tasks and also for these reinforcement learning or maybe interactive workloads and things like that. And the whole design makes it very easy for the system to be fault tolerant. So here's an evaluation on an end-to-end reinforcement application. Here we chose a system called Evolution Strategies, which is being developed by OpenAI. It's a derivative-free optimization for doing reinforcement learning. And they have a system that they use internally. It's a Redis-based system. And with Ray, we can actually, so here we have a plot of the mean time to solve the problem. In this case, it's a robotic task where you learn walking, basically. And then here's the number of CPUs being used for the computation. And both on Ray is the blue bar. It's faster than the Redis-based solution, and it can also scale much higher, up to 8,000 cores, which actually gives a new state-of-the-art result on this benchmark. And then here's another one. This is comparing against the very highly optimized MPI-based baseline for reinforcement learning, again, for an algorithm called proximal policy optimization. And here, actually, we can beat, with a generic system, we can beat a special purpose system, which is very nice. So let me now talk a little bit about applications and libraries that we have been building. Because systems are only as good as the applications really that they enable. And so on top of the hardware resources in the cluster, there's the Ray tasks and actors. And on top of these, we have been building a bunch of libraries. So one is Tune for doing hyperparameter optimization, which abstracts away all the hardware resources. It supports heterogeneous compute, so you can have arbitrary GPU, CPUs, accelerators, things like that. It also supports stateful hyperparameter optimization algorithms like hyperband or population-based training. Then we've been building a library called RLlib for distributed reinforcement learning. There's papers about both of these libraries if you are interested in learning more. And then we are also building a data processing library called Pandas on Ray, which has the same API as Pandas, but makes it very easy to scale up the data processing. And then currently we are working on a library for distributed SGD on top of Ray. So there's an increasing number of production use cases. Ray is now being used at a number of companies. I'm going to highlight some of the applications. So, for example, Unfinancial is using Ray for graph processing, for fraud detection. Here, Ericsson has been doing a bunch of work on antenna tuning with Ray. At Berkeley, there's a number of projects using it. One that I want to highlight is one for mixed autonomy traffic. So what they are doing is they are studying the regime where there's a mixture of human and autonomous drivers on a highway. At the moment, this is mostly in simulation, so they have many simulators. And then they can use RLlib and Ray to train autonomous agents that can interact with the human drivers and lead to the traffic being much more efficient, because the autonomous vehicle can sort of route human drivers and can therefore improve the efficiency of the traffic. There's many others in robotics. At Stanford, people are using it to learn more intelligent SAT solvers and things like that. So Ray is open source. It's available on GitHub. And it's very easy to install. You can just do pip install Ray. And I encourage you, if you have distributed AI workloads, to try it out. We have had a growing number of contributors since our initial release in May 2017, and we have now more than 100 contributors. Okay, there's a bunch of related projects that I wanted to mention. So one is Spark, which is a bulk synchronous parallel system. Spark is more centralized on stateless computation. It also doesn't support nested tasks and is more optimized for coarse-grained tasks. Then there is also actor systems, for example, Orleans or Erlang. These are typically focused around implementing an actor model. They're very scalable, but they typically don't provide fault tolerance, no transparent fault tolerance, and also lack support in more data-heavy workloads. Okay, so to conclude, the new emerging AI applications require unifying the ML ecosystems because typically they require computations, different computations, for example, training, model serving, streaming, or data processing. And we provide a unified system for supporting all these workloads by unifying stateless and stateful computation, and also providing a unified fault tolerance model. The system is horizontally scalable at all levels, and so provides very high throughput and low latency tasks. So as a takeaway, Ray can outperform special purpose systems for these cross-cutting AI applications. And thank you for your attention, and I'm happy to take questions.
Thank you. Do we have any questions for the speaker? Got a question over there.
Yeah, sorry. In the last slide, you showed that 2 of the top applications that the companies are using are basically for the graph data. Mm-hmm. Yeah, here, like Intel, ETL for graph structured and financial. So can you give a short, like very brief guidance, like how one can use Ray for the graph data?
Yeah, so for graph data, it's very important to support these sort of very low latency operations, because oftentimes you only touch very few of your data. And so what you can do with Ray is you can just keep the data in memory, and you don't need to serialize the graph or anything like that. You just keep it around as actors, and then you can define tasks on them that do things like, for example, walk the graph. What Financial is doing, for example, is they are doing fraud detection, so they have to find cliques, and they have to see what are the paths where money is routed through, for example. Then you can build these sort of systems that do very low latency operations on graphs. And so Ray is a system that is very well suited for these sort of applications.
Any other questions? Oh, one in the back there.
Great talk. I have 2 questions. How deep of graphs can you handle if they're generated somehow? And how is the scheduling done to help with shuffling data, too much data, to keep it where it should be optimally?
So in terms of how deep the graphs can be, it depends very much on how you implement it, I guess. If you can like batch together things, or there's various techniques how you can. I mean, it depends very much on what the operations are, so I can't really say it generically. It depends on application. In terms of the scheduling, so we have this. I'll go back to the architecture slide, and we have this way to do. Distributed scheduling. So if a new task arrives, the scheduler will first determine if the task dependencies are available locally. If yes, then it will see if there's available resources. If both of these are true, then it will try to schedule it on the local node. So it will find a new worker on that node and then assign the tasks. If not, it can look up. We have a table of data dependencies and where they live in the cluster. That's stored in the global control store, and that it can find out where the dependencies of the tasks are. If there's a node available that has the dependencies and also available compute, it can schedule them there. Otherwise, it will just find another node which has available resources, and then will transfer the data there, and then the task will be executed.
All right, thank you.
Thanks.
Any other questions? Okay, if not, let's thank the speaker again. Thank you, Philipp.